Thank you very much, Randy, for this wonderful introduction. And thank you very much to the Keck Observatory for making this happening, for the invitation to this prestigious lecture series. And indeed, I was looking forward to this talk today, and I hope that there will be other opportunities to tell you more about new research that I'm able to do, hopefully, in the time I am here. What I will talk about is a lot of stuff that has happened in the past years with my research on black holes, but as you will see, there are also very tight connections with the Keck Observatory that has played a major role in my career. I'm also very proud and glad that part of my family is here, my wife, my mother, my auntie, and the Keck Observatory has actually played a role in bringing us here, and so I'm really glad and thankful. Black holes and the fate of the universe. Randy has already referred to the book, The Fate of the Universe. It's actually, unfortunately, not available in English yet. It's only in German, and I have not yet found the time to translate it into English, but that is still on my to-do list, so I hope that things like this public lecture can motivate and give me more time to do that. But it is a little bit about the story of everything from the beginning to the end. And this is the theme that I also would like to stand on tonight. But I want to focus it on what role the black holes actually had in the fate of the universe and what black holes are, how we can understand them better. So let's start out with the question, what are black holes and how do they form? A black hole is actually something very simple. It's just an area of space which is so thick, so heavy, and so dense that it is able to eat light. I mean, in addition to everything else, it's able to attract light and not let it out again. And what you see here is an artist's concept how a black hole would look like in front of the Milky Way. And the black hole that you can see is actually what you can't see. The black hole itself you can't see, but you can see the effects that the black hole has on its environment. So when we are talking in astronomy about black holes, we don't speculate about what is inside, but we can draw inference from astronomical observations what is outside the black hole, and by that we can then infer that there must be a black hole. A black hole is probably the most simple form of a celestial body that you can think about. A black hole can actually be described by three numbers, by mainly the mass of the black hole, which is the biggest contributor, but then also a black hole can have a charge, it can be electrically charged, and a black hole can have a spin, so it can rotate. But for this simple introduction, let's just look at the mass of a black hole. Now, I promise you there will be not many formulae in this talk, actually only the formula on this page, but I need a few equations to at least motivate that we are physicists and not just dreaming about the sky. So the first thing is the escape velocity. When you are throwing something, if you take something and you throw it up, you will see that it arises and then it stops and then it falls down again in a parabola. But in principle, if you give this body a certain speed, then it can escape the Earth, and that is the speed that you, for instance, have to put in behind a rocket in order to leave the Earth. In the case of the Earth, this is 11 kilometers per second. And so for every body, you can in principle calculate the escape velocity, and the only two quantities that go in there is the mass and the radius of the body. And so you can in principle, if you would, for instance, take the Earth and you make it smaller, if you take the Earth and you squeeze it together by a factor of 2, you make the radius smaller, and automatically the escape velocity gets higher. And so there have already been many 100 years ago, there have been people thinking about the escape velocity. How small do I have to make a body until this escape velocity gets to the velocity of the speed of light? And as soon as the escape velocity gets the size of the speed of light, nothing can escape this body, not even light. And so there have been already before Einstein, there have been people thinking about dark stars, which are so compact that they don't let light escape. And this is in principle what we call a black hole. Now Einstein then came along 1916 and made the prediction that space is actually curving, mass is curving space. So if you are putting something in empty space, it has the tendency to curve light rays around. And this is what is indicated here in the next graph, the light bending. If you take a star which is close to the sun, then the gravity of the sun is actually curving, bending the light around the sun. And Einstein has made this prediction that this should be measurable if you measure very accurately at a solar eclipse when the sun is not visible itself, then you could measure the stars behind the sun and you can see them shining a little bit closer together than if the sun were not there. And this has been then discovered by Eddington in 1919. And then that was what made Einstein famous because he made this prediction which was finally proven, and the theory of relativity that Einstein has produced is still basically unchallenged. It is still the theory that we are living on today. Everybody in his GPS system, when you have your navigation system on, is relying on Einstein's equations. And so the black hole is actually something which naturally drops out of Einstein equations. And it's very simple. If you take the same experiment, but now you make the sun a little bit smaller, say you squeeze the sun down to half of its radius, what you will see is that the curvature is getting twice as big. So the curvature is dependent again on the ratio between the mass and the radius. And if you have something which has a smaller and smaller radius, the curvature gets larger and larger. And you can calculate what is the size that a body has to have, that the curvature is actually such that light is curved around the body in the same way as we have it here, where light cannot escape this body because it is curving around space. And this is again the same quantity that you can calculate by the escape velocity. And this is the final answer. The radius of a body that we call a black hole that doesn't let light escape is a very simple quantity where you just divide the mass by the speed of light in quadrature, and you can calculate very easily how much you have to squeeze a body in order to make it a black hole. So every body can be a black hole if you squeeze him enough. Be careful. So in the case of the sun, this is actually a radius of 3 kilometers, and that is about 1 million times smaller than the current size of the sun. In the case of the Earth, you have to squeeze the Earth down to 1 centimeter to make it a black hole. So you really have to put a lot of pressure and squeeze very much. And so the question is there anything in nature, I mean, are there any forces that can really squeeze a body so much that it can become a black hole? And it turns out, yes, there are forces in nature, and gravity is the strongest force that can actually squeeze down matter so much that the light cannot escape. Now, there is a very ambitious, I mean, you might have realized from the title of my talk, I'm not shy of using ambitious words and ambitious graphics. This is a graphic which is actually putting everything in the universe from the smallest body, from the much smaller than an atom, to the biggest size of the current universe into one graph. And this body is giving the mass and the radius, so these two quantities that are going into this equation, the mass and the radius. And they are giving it in units of a proton radius. So this is 1 proton is down here. It has the mass of 1 proton and the radius of 1 proton. And then you can put a few things. I mean, you can basically put everything that we know of into this graph. I have just put a few things in here. Humans are about 10 to the 19 protons and the size of about 10 to the 25 or so protons. If you take the Earth, you are up here and the sun is up here. And then you will see that bodies that you can actually take into your hand or you can look at, they follow this line here, which is the atomic line. And the atomic line is that the mass of something is about the third power of the radius. You're measuring the mass with the volume of a body, and therefore you have the normal stuff going up here. nuclear matter, like the center of atoms, or also something like a white dwarf or a neutron star, is almost following that line but shifted to the left because it is much more squeezed down. The black hole equation, the Schwarzschild radius, is this one, where basically mass and radius are linearly dependent on each other. And so everything which is on this line is a black hole. And then there is another line down here. This is the quantum mechanical line. This is what is governing the minute world of atoms and quantum mechanical fluctuations. And that is actually funny. Something gets more massive if you squeeze it further down. So in quantum mechanics, the life and world is completely the opposite than in normal mechanics. And so there are bodies which are close to a black hole. And here the smallest object that you can think about is exactly at the intersection between Einstein's theory of relativity, which is the gravity line, and Planck's theory of quantum mechanics. And actually it turns out that at this location where I wrote this called the so-called Planck hole, at this location our current physics breaks down because Einstein and all the physicists after him have not succeeded in getting one theory which is actually describing both the quantum mechanical and the relativistic regime. And so the Planck hole is still a big uncertainty, but everybody believes that at the scale of a Planck hole, this is actually where our universe was formed. And I will come to that in a minute. So our universe was formed somewhere very, very close to a tiny Planck hole. And so it was in the beginning close to a black hole. And if you now put our universe on this scale, up here, the mass and the radius of the universe, it is still very close to a black hole. Our universe is almost a black hole if you look at it from the outside. It's not quite a black hole because we now know that the mass is not sufficient to bend light enough to not let it escape from our universe, but it's reasonably close. And so then there are a few things like stellar mass black holes. These are black holes that are coming out of normal stars. And then the so-called galactic black holes, the supermassive black holes in the centers of galaxies, which are in the course of the universe have been developed. But in this line, it is shown that there are things in the universe, and the universe itself is actually dangerously close to a black hole, that black holes are not really such a bizarre thing to think about. Now let me come to the cosmic evolution. I don't want to dwell too much on cosmology and evolution, but I think it is important to put everything in this context. I said the universe starts close to the scale of a Planck hole. There is a time associated with the Planck time, which is 10 to the minus 43 seconds, which is a minute time. And there is a Planck mass associated with the black hole. And this is where we believe the universe started. And then the life of the universe, in very simple terms, is nothing else than by continuous expansion, it's getting larger and larger, but it's also getting colder and colder. And on its way down from getting colder and colder, more and more things are freezing out, which were not able to live in the early days because it's too hot there. But when it's getting colder and colder, then matter can freeze out, and then later planets can freeze out, and later lakes with water can freeze. So the history of the universe in large terms is nothing else than a continuous cooling down with more and more complicated structures being able to survive. Now, we have to talk a little bit more about the fascinating physics that happens close to the so-called Planck hole, where quantum mechanics and gravity, quantum mechanics and very strong gravity are playing an important role. And there it turns out that black holes can teach us something very important. And this is what Steve Hawking has developed, namely that black holes can not just eat matter and eat light, but on the long run, black holes can also radiate. So black holes can actually give back to nature all that what they have swallowed. And this is through the Hawking radiation. And the Hawking radiation is connected to quantum mechanical quantum fluctuations in space. this is again another very complicated topic, but from quantum mechanics we know that there are many things that you cannot measure accurately, because whenever you measure something you are getting a so-called uncertainty principle. If you want to measure an energy level, you cannot measure it to the absolute precision, because whenever you measure it, nature is somehow flickering around a certain value. And if you try to measure the energy of zero, which is basically the energy of empty space, then quantum mechanics predicts that the energy of zero is also not well defined, and that it is actually flickering around in a quantum mechanical uncertainty state. And this is interpreted or visualized in quantum mechanics as so-called virtual particles, which are created out of nothing. They live together for a short time, and you have to create two particles, a particle and an antiparticle. And as long as they are just living for a very short time and then they destroy each other again and they give back the borrowed energy to the vacuum, then this is what quantum mechanics actually requires. This is the way how you can envisage that empty space is filled by stuff, by something, which are these virtual particles. And if you are trying to measure the energy of space, then sometimes you measure a particle, sometimes not, and that is giving you this fundamental uncertainty that quantum mechanics requires. Now this is all well, but now what happens if you are putting a black hole into this empty space? If you put a black hole into the empty space, then it can happen that in such a virtual particle, one of the partners of the particle is actually swallowed by the black hole, and the other partner is then finding nobody to annihilate with. I mean, it doesn't find its partner back to give back the energy that it borrowed, and therefore this particle all of a sudden turns into a real particle. So it is all of a sudden interacting with the real world, and it's going out, and it's radiating away from the black hole. And so it can happen that, for instance, if this particle is close to the event horizon of the black hole, it is one of the partners is swallowed, the other one is going away. And that means that the black hole is losing energy in a sense, because the empty space around the black hole has to somehow pay back the energy that was borrowed by the particle when it was created, and then the black hole, while it is eating some of these virtual particles, it actually radiates real particles, and so it's losing energy. And if you wait long enough, then this black hole will actually lose so much energy that it is very quickly going down in mass, and then in a kind of explosion of energy, it is dying, and it is evaporating into empty space. And so black holes, in principle, don't live forever. Black holes take a while, and it takes a very long while, namely 10 to the 60 to 10 to the 100 years, before they finally evaporate. And so in that sense, black holes are the longest lived species in our universe. There's nothing which lives as long as black holes, because all the other parts of matter will long be gone. It may actually very well be that in this long period of time, several other universes have already been created and have already been lost, but the black hole is still living for a very long time. And what Stephen Hawking has told us is that there is an intimate connection between quantum mechanics and gravity in the connection with the virtual particles in empty space. And now this is something which is also playing a very important role in the beginning of the universe. When the universe was formed out of a very tiny spot and very tiny piece of vacuum, we believe that the universe was formed out of a quantum fluctuation in space-time. So the universe is just one special, very special quantum fluctuation which was drawn out of a zoo of quantum fluctuations that are filling empty space. We believe that a very, very tiny piece of empty space, which is filled by these fluctuations, all of a sudden, by some force which we do not yet fully understand, but all of a sudden was ripped apart and was blown up into something of the size of a soccer ball. And the fluctuations which were in this original quantum fluctuating space are still visible today in this baby picture of the universe, which I show here as a microwave background radiation picture. And what happened is that from these original, let me go back to this diagram, empty space is filled with these virtual particles. If all of a sudden you are pulling away empty space, then that means you are blowing it up very rapidly into something much bigger, then every one of these virtual particles is pulled away so far that it cannot find its partner again. And all of a sudden, you are pulling out a zoo of real particles from empty space. And that is what inflation has done in the beginning of the universe to our space, out of which the universe was created. And so the simplified picture is that a very, very small piece of space of the size of a Planck hole was ripped apart, was pulled out to something of the size of a soccer ball. And all the virtual particles, the pairs of particles that were in this little empty space, have been pulled into real particles, which became a very, very hot so-called quark soup, a soup of particles and antiparticles, which then were expanding larger and larger and were cooling down further and further until today's galaxies, stars, and so on have been formed. All of this is pretty difficult to understand. I don't understand it all myself, but just get away from this talk with the knowledge that virtual particles, empty space, gravity, and so on are all intimately connected in the beginning of the universe. Now let me come to real black holes. Real black holes, we believe, or I think we pretty well know, that stars at the end of their life, certain types of stars at the end of their life, can produce black holes in their center. What is shown here is the normal life of a star, which is formed out of a gas cloud, like the sun was formed out of the pre-solar nebula. This is the sun here, and the sun, and each of these little bullets is one time step. So the sun is living for a very long time. It's living for about 10 billion years. It is currently roughly in the middle of its current life. And if you follow it along for about 5 to 7 billion years more, then the sun will turn into a red giant, a very big red star. And in the end, the red giant will blow away its atmosphere into one of these beautiful planetary nebula that we can see in many astronomical pictures. And in the end, the ash of the burning oven in the center of the star, the sun is burning hydrogen into helium. The helium is forming a compact body in the center of the sun. Then sometimes the helium starts to burn. It is forming an even more compact object. But in the end of the solar life, a white dwarf will remain. And a white dwarf is something of the size of the Earth, roughly, but of the mass of the sun. So you can imagine this is already a body where the sun has been squeezed down by roughly 2,000 times its current size. And so the whole mass of the sun is into a body which is much, much smaller. And so we are already on the way to the black hole, but this is not yet sufficient to really bend light enough to not let it escape. If you have even more massive stars, like for instance a star of 10 solar masses, then it lives much, much shorter, it shines much brighter, and so everything goes much faster. And in the end, it is producing a red giant again, but it then does not blow off its atmosphere in such a cozy fashion as the sun. It is actually exploding in a supernova explosion. And in the end, again, a compact body is formed, and this body is called a neutron star. A neutron star is about the size of a big city like Honolulu or so, and it has the mass of the sun. So all of a sudden you have squeezed down the mass of the sun into a body which is very, very compact, roughly the size of a big city. And the density of the material in the neutron star is already close to the density of the nucleus of an atom, where you are putting together many protons and neutrons to form an atomic nucleus. The neutron star is basically a huge atom, which is about as I said, the size of a city, but the mass of the sun. And the neutron star is already a body where the light is now turned around, not 360 degrees, but something like 90 or 180 degrees. So the neutron star is already relatively close to a black hole. But this is not the end. If you have a star which is even more massive than 10 solar masses, if you have something like 30 solar masses, then in the end, the mass which is in the center of the star, the compact mass, is so large that not even a neutron star is a viable solution anymore. And then you have the compression of gravity is strong enough that in the end you are producing a black hole. So here we have a white dwarf, a neutron star, and then finally, in the most massive stars, black holes are formed at the end of their lives. We can, in principle, watch this phenomenon in the so-called gamma ray bursts, where in the center of a star, a neutron star, and then a black hole is formed, and the black hole is then able to basically drill a hole in the star from the inside out, and you are ending up with a single black hole that is formed at the end of the life of a star. These gamma ray bursts have caused a lot of excitement the last, 15 years ago or so, the first time we really realized that these explosions that we see in the sky happening every once in a while, every day, typically somewhere a star is exploding and turns into a black hole. In the meantime, these gamma ray bursts have actually been turned into the lighthouse of the objects that are the furthest away from us in the universe. They can be so bright that they can be really observed towards the very, very distant edges of the universe. And this curve here on the right of this graph shows a kind of history of the record holder of which object we know that is the most distant away from us. And so it starts roughly in 1962 when my colleague Martin Schmidt discovered the quasars. And the quasars, they are, and we will come to them, they are black holes in the centers of galaxies. They are incredibly luminous, and so they can be observed very, very far out in the universe. And very quickly the quasars became the record holders of the most distant objects. And roughly until 1990, this is when the Keck telescope started to observe here in 93, 94, the quasars were actually still the most distant objects in the universe. This scale here is called redshift. It tells you how far the light is actually redshifted by the expansion of the universe. A redshift of 5 means that the light is actually redshifted 6 times its own wavelength, so it's turned from optical light into very, very far infrared light. Then the Keck telescope came along, and normal galaxies all of a sudden started to become observable and became as distant as the quasars. And for a while, for a few years, the galaxies and the quasars actually had a race where every 1 year another object had basically the lead. And then in about 98, 97, the first gamma ray bursts were discovered and were identified. And very quickly, the gamma ray bursts actually took over. And now, today, the most distant objects that we know are not quasars and not galaxies, but gamma ray bursts. These events when the black hole was formed in the early universe. In the meantime, the highest redshift quasar and the highest redshift galaxy are around a redshift of 7. And then the most believable gamma ray burst has about redshift of 8.2, but there are some which believe that there is also one at redshift 9.4. And so the telescopes on Mauna Kea, Keck, and also Gemini had a very important role in this record history for the most distant object. And black holes, both the quasars and the gamma ray bursts, are actually in the leading edge there. Now let me turn to the question, how can you feed a black hole? Because when we are talking about stellar mass black holes, these are the ones where we understand how they actually are formed at the end of the life of a star. But what we are observing in the centers of Milky Ways are black holes which are a million to a billion, even 3 billion times the mass of the sun. And so they are not stellar mass black holes. They must have swallowed millions and billions of stars in order to grow that big that we are observing them today. And so a very important question is, how can you feed a black hole to become so fat and so thick so quickly? And this is still a very large field of research. And this is one where I had the pleasure to also collaborate with a few people and make some interesting discoveries. But this is also an area where the Keck telescope played a major role. When we are looking in the center of our Milky Way, in the center of our own Milky Way, we now know that there is a black hole. And there were two groups of astronomers, Andrea Ghez in UCLA, and my colleague Reinhard Genzel at Max Planck Institute for Extraterrestrial Physics, which were friendly, competing, and cooperating in discovering this black hole and studying its nature. And so let's have a look at the center of our Milky Way. This is actually the constellations Sagittarius and Scorpius that you can beautifully see tonight if you look out later at night. And this is now zooming in into the very center of our Milky Way, where you now see the fainter and fainter stars closer and closer together, and you need better and better technologies to really observe and resolve these stars. And adaptive optics, as we will see on the Keck telescope and also on the Very Large Telescope in the Southern Hemisphere, have played a crucial role in finding out more about the very, very center of our Milky Way. So the area that we are looking at is actually an extremely tiny spot, just a few 10 arc seconds across, in the very center of our Milky Way, which is embedded in a huge star cluster, and you can only observe this in the infrared wavelength band, because in the visible there are all the dark clouds that are in front of you. And this square is the one that has been studied for many years, both with the Very Large Telescope and also with the Keck telescope. And this is the one where these two groups, Andrea Ghez and Reinhard Genzel, have found stars which are moving around the black hole in a regular fashion. So this is the movie from Reinhard Genzel's group, and this is more or less the equivalent movie from Andrea Gez's group from the Keck telescope. And this picture from the Keck telescope was actually taken this year, when for the first time Keck was observing the galactic center with both telescopes, with both Keck 1 and 2, and with adaptive optics, both observing simultaneously the center of our Milky Way. And the net result was that there is the stars which are moving around the black hole almost, I mean, with extremely large speeds, with about 2,000, 3,000 kilometers per second. And they form what Kepler has already predicted long ago. They are making wonderful ellipses around something which is invisible, and this is the black hole in the galactic center. So let me turn this into something more visible. What they have calculated from these orbits is that the mass of the center of the black hole in the center of the Milky Way is 3.5 million solar masses. So 3.5 million stars have been already fed and eaten by this black hole in order to grow to that size. This is how the whole thing looks from a more public eye. This is from a NOVA film, where you are zooming into the galactic center. You see the gas and dust clouds which are swirling around in the center. It's a very, very interesting and exciting place. And you have then the stars which are swirling around the black hole when you zoom in. And you see the black hole itself is almost not visible, but you can see the stars while they are wandering around the black hole. When you look here at this corner is where we believe the black hole is. And indeed, the surrounding of the black hole itself is also radiating, but it's radiating very, very slowly, very, very dim, so that you can only see it by very detailed measurements that I'll come to in a minute. This is how we know our galactic center today. There are about 25 stars whose orbit is exactly known, and they all orbit around the center of the Milky Way. Now there is a big problem, and that is if there are so many stars swirling around this black hole, and we know that stars, for instance, are giving out winds. Stars are like our own sun, and even more, these massive stars which we see in the center of the galaxy, they blow out winds like crazy. And these winds, solar winds and stellar winds, they should in principle provide enough matter that the black hole should happily eat and should actually be very bright and visible by normal techniques. But the black hole in the center of the Milky Way is about 10,000, 100,000 times fainter than you would expect it to be by simple calculations. And so it turns out that the gravity around this black hole is playing a major role, and it is also preventing matter to fall down on the black hole. And this is because of the angular momentum barrier. You know, when an ice skater is drawing these pirouettes and it is rotating, she is pulling, or he is pulling the arms in and then rotates faster and faster. And this is the conservation of angular momentum. Basically, if you pull stuff in, you have to rotate faster and faster, and that in the end doesn't allow the matter to fall in completely. That's the reason why, for instance, the rings of Saturn don't fall into Saturn. I mean, they are happily circulating around Saturn. That's the reason why the Earth doesn't fall into the Sun, because the Earth is stable on its orbit around the Sun. And that's also the reason why in normal circumstances it's very hard to bring matter down to the black hole, to squeeze it down to such a small diameter that the black hole is. And this is indicated by this movie, which is a PhD thesis of one of our graduate students in Garching, Jose Quadra, who was calculating the physics of these gas masses, which are this. I mean, the black dots here are the stars. Let me go back once more. The black dots are the stars. Each of these stars is blowing out a wind of a gas stream, and in principle, the black hole is down here. And so he was calculating what happens to this gas. Why doesn't it come down to the black hole? And so if you look in detail, then after a while, the gas masses are actually starting to swirl around the black hole. They are forming a disk. But when you look in detail, then this disk has a hole in the center. And this is almost like the rings of Saturn. The rings of Saturn don't fall down to the Saturn. This gas doesn't fall down to the black hole. It's very hard to actually squeeze the gas down to the black hole in order to let it grow. So you have to have very, very special conditions, very, very thick matter or some special event that happens in order to bring stuff down to the black hole, because the angular momentum keeps it from falling in, the same way as the angular momentum keeps the Earth from falling into the Sun. So what can happen to make a black hole really happy and give it something to eat? In the years around 2003, all of a sudden several different groups have found that the black hole in the galactic center is actually at some point flaring up, typically once a day. It is getting brighter, and you have seen here a movie, an X-ray movie, where all of a sudden the X-ray flux of the black hole in the galactic center is increasing by a factor of 50. And here you see an infrared movie from the Very Large Telescope in the south, where you see this, the center here sometimes getting brighter and then dimming again. And so roughly every day the black hole is taking a snack. And if you calculate the amount of matter which is falling into the black hole, it's about the size of a mountain or a comet or something like that. Mount Everest, one Mount Everest per day is swallowed by the black hole in the galactic center. We do not yet completely know what exactly happens there, but we believe that some gas masses are still able to fall down to the black hole, and every once in a while it's taking a snack. And so we can really watch the center, the galactic center black hole, taking its snack. And this is actually what was observed by Andrea Ghez and her collaborators this summer, when they pointed the two Keck telescopes onto the black hole with the two laser guide stars, and they were actually measuring simultaneously in two different wavelengths the color of the light of these snacks that the black hole was taking. Now there is something happening out there right now, something extremely fascinating. More food is arriving, as I said here. When you are looking in detail at the measurements, at the astronomical pictures of the galactic center over the last 10 years, a colleague of ours in Garching, Stefan Gillessen, has actually found a fascinating object, a gas cloud, which is currently moving towards the galactic center. If you are zooming into this picture, you can see in 2004, the gas cloud was here, 2005, it was moving, 2006, 7, 8, it is moving towards the galactic center, whereas the other stars are rotating around it. And so what we believe happens is that you have the stars which are swirling around the black hole, but there is also a gas cloud which is coming in from outside, and it is approaching the black hole, and soon, roughly 2014, it will come very close, and then the black hole will actually start for many years, for about 20, 30 years, to get to shine brighter, because it has actually new food is coming. And so nature finds a way to actually overcome these tidal forces. One of them is that whole gas clouds or whole stars are actually swirling so close to the black hole that they then finally can be eaten. And such a phenomenon can also be seen not in our own galactic center, because that happens only every about 100,000 years. But if we are observing many, many different black holes in different galaxies, we can sometimes find a whole star which is actually coming close to the black hole, and it is swallowed by the black hole, and then the black hole is shining up, it's brightening up by a factor of 10,000. So we have actually a few years, 10 years ago, we have observed several of these objects where there was nothing before, and then all of a sudden the object became extremely bright in the X-rays, and then it decayed and it died out. And what we believe, what we see here is a single star, a poor little star is coming so close to the black hole that the tidal forces of that black hole are actually disrupting the star. And you can see this here in this movie down there. Poor little star on its last orbit. So one of the stars circling around the black hole in the Milky Way will also experience this fate, that at some point it's getting so close to the black hole that the black hole is strong enough to rip it apart. And then some fraction of that star will actually be eaten by the black hole, and then the black hole for a long time, for 10 years or so, will become very bright and shining happily. This event, which we call a stellar tidal capture and disruption event, is actually currently happening in one object that has been discovered by Pan-STARRS, by the Pan-STARRS telescope on Haleakala and by the GALEX satellite. The Pan-STARRS telescope on Haleakala, this is a beautiful picture of Pan-STARRS, and here in the background we see Mauna Kea, where our Keck telescopes are. Pan-STARRS telescope is making a movie of the sky, and it's triggering on anything that is actually special. It triggers on moving objects like asteroids, but it's also moving on supernova explosions where on one night there is no star, and then on the next night there's all of a sudden a star. And this Pan-STARRS telescope has discovered one of these tidal captures in the act, which is still going on right now. And so this is the movie, the simulation, what we believe Pan-STARRS has seen. This is the black hole, and the star has turned around, and in the course of about 100 days or so, the star is completely disrupted, and matter is falling into the black hole, and the black hole is shining happily because it has gotten something to eat again. So this is the way nature can, in principle, feed a black hole and feed single stars into a black hole, but it is actually a relatively tedious way. It can only eat a certain amount of snacks. It doesn't eat. I mean, some of the black holes can eat whole stars, but it happens only every 100,000 years or so. So it's not really a very efficient process to feed a black hole. There are much more efficient processes, and these more efficient processes are connected to extreme events when whole galaxies are actually colliding. We are coming to that in a minute, but let me now invite you to a journey through our local universe, where we are traveling from our own Earth to a place in our local universe which has an extreme high concentration of mass. What we are seeing here is a kind of map of our local universe. The universe is consisting of this three-dimensional filamentary structure which we call the cosmic web. And this picture is tuned in a way that we are sitting here. This is a zoom in onto our local neighborhood. So you are here. And our next big thing, the next big city, so to speak, as viewed from us, is the Virgo cluster. It's a cluster of galaxies in the constellation of Virgo. And this is where I would now like to invite you to a journey where we quickly, with about 26,000 times the speed of light, we are moving there. Completely, I mean, impossible, but imaginable on the computer. So, here's the sky. Who has discovered this constellation? This is Orion, that you can see tonight, closer to the morning. We are now flying to Orion and fly towards the center of our Milky Way. This movie has been made by Brent Tully from our institute, and it comes with music. Strauss. Thank you. So, for some reason, Strauss needed to know exactly how long this travel was to make this music so perfectly fitting. So, we are now arriving, we have arrived at the center of the Virgo cluster. The galaxy in the center of the Virgo cluster is M87, Messier 87, and it is actually a galaxy which is about 3 billion solar masses, so it's about 1,000 times bigger than our own Milky Way. And it contains, the galaxy is about 1,000 times bigger than our own Milky Way, and it contains a black hole in its center of 3 billion solar masses, which is about 1,000 times bigger than the black hole in our own Milky Way. So actually there is a relation between the galaxies. If you have a big galaxy, you have a big black hole. If you have a small galaxy, you have a small black hole. On the way to the Virgo cluster, we have seen several thousand galaxies. These galaxies that we have seen have all been pictures from the Hubble Space Telescope, or almost all. We have also seen a few objects like the Orion Nebula, like the Crab Nebula in our own Milky Way. But then we left the Milky Way and we have seen zillions of galaxies which were oriented in a kind of filamentary structure, and we were moving to the center of this Virgo cluster. And this object, when you look in detail, then there is a little streak here, which is actually a jet. And when you look in more detail, this is with the Hubble Space Telescope, this is with radio telescopes, with X-ray telescopes. You see a bizarre structure, which is an extremely long jet that goes out many times further than the Milky Way itself. And it is actually a needle-fine jet which we believe is consisting of relativistic particles, particles that are moving out with the speed of light, which are ejected from the center of this galaxy. And this is what we call an active galactic nucleus. An active galactic nucleus is a black hole in the center of a galaxy which for some reason is eating matter happily and then is also spitting out some matter, and it's able to make these jets, which we have already seen at the beginning of the talk. A black hole, for some reason, very likely due to the magnetic effects in connection with the rotation of a black hole, is actually able to drill holes into the star that we've seen before, and it's able to drill a hole into its environment. It's ejecting a jet. And so the next film that is also coming with music, I'm sorry. This is now the Fifth Symphony of Beethoven, the symphony called the Fate Symphony, Schicksal Symphony. This is again trying to motivate what the center of a galaxy with a black hole is looking like. What we will see is a black hole that is actually eating stars continuously. Every year one star is eaten, and so this is a black hole that is really extremely happily fed, and it's growing and growing at an almost exponential speed. So let's have a look at this black hole. A very nice movie that was made by Wolfgang Stephan at the University of Guadalajara, Mexico, and it was showing a black hole, not just an artist's concept, but in real physical terms, what we believe what happens in the center of this black hole. There is an accretion disk, so the matter is actually swirling around in this disk, but contrary to the Saturn rings, this disk is so thick that actually the particles are continuously hitting each other, and there's a lot of friction, and by this friction there's actually heat produced and energy lost, and then the matter is slowly drifting inward and it is swallowed by the black hole. And every once in a while the black hole is actually not able to eat all the matter that is swallowed down into the funnel, and then it is actually getting a kind of hiccup and is ejecting relativistic particles along the jet that we have seen. And so this is, if you have a black hole which is actually happily eating and fed. And so in principle we know that this is possible. We observe objects like that. It's very rare. Only 1 in 100 or 1 in 1,000 galaxies is actually doing this at any time. But we know that it is a very important process and moment in the life of a galaxy. And now we just have to understand why is it that there is all of a sudden so much matter in the center of the galaxy that the black hole is actually happily swallowing stars by the year, so to speak. 1 star every year for 100 million years or so, and it's growing very, very rapidly. And this is connected to the concept of merging black holes and merging galaxies. On our trip to the Virgo cluster, we have seen many, many galaxies, and some of them were actually entangled in a dance around each other. And this is when 2 galaxies are coming so close to each other that by their own gravity, by the gravity of the dark matter, which is holding the galaxies together, they are actually pulled in and they are merging. Some people call this galaxy cannibalism, so as if they would eat each other up. I call this a galaxy marriage, because 2 galaxies are actually joining forces together, make an even nicer and bigger galaxy. And this is what happens relatively frequently, typically once in the life of a galaxy. It is actually merging with another galaxy, and then fantastic things are happening. We now believe that every galaxy which is big enough has a black hole in its center, and when these 2 galaxies are merging, then the 2 black holes in the end will also merge. And this was a prediction by the theory that you should actually see sometimes binary black holes. You should see galaxies that do not contain just one black hole, but two. And indeed, our group in Garching in the year 2003, with Stephanie Comossa as a lead author, has discovered the first binary black hole, the first black hole that is actually two black holes in one galaxy. This is the galaxy that we are talking about, telephone number 6240, but it has in the meantime become very famous in astronomers' terms. And what we see here is actually something like a train wreck. Two galaxies have crashed into each other. There is two nuclei. In the meantime, there are much more beautiful pictures of that galaxy. And so you see this is a Spitzer and Hubble image of that galaxy. And there are two nuclei from the old two galaxies that are so close together that they are now entangled and intertwined in a dance around each other. We have actually pointed the Chandra telescope, the X-ray telescope, which is still up there, observing with very crisp resolution the center of this galaxy. And we have found two hard X-ray sources, which very likely are two black holes. In the meantime, Chandra has observed this much, much longer. And there's no doubt about now that there are two black holes which are actually circling around each other. And it will take about 100 million years until these black holes are coming so close together that they will actually then finally merge into one big black hole. And so what we believe we see are two galaxies that are coming close to each other. They are rushing through each other, train wreck. The stars are completely reoriented, and then in the center of this galaxy there are these two black holes, and each of them is now eating happily from its environment because there is so much gas and dust and stars and so on in the center of this train wreck that the black holes can now just grab whatever is there, and they can grow and they can eat happily. And that's, we believe, the way how you can actually make big black holes out of small black holes. And in the end, you merge them, and then actually the whole space is shaking. There is a phenomenon that is also predicted by Einstein's theory that gravitational waves should actually be ejected, and then the whole space is kind of rippling by the action of these two black holes. This has never been seen so far, but we hope that in the next 10 years we will see gravitational waves from similar effects, and so this is also a fascinating subject. But finally, it was realized that these black hole mergers can and must play an important and very important role in the evolution of galaxies. And there has been a whole industry formed, of people who are trying to understand what exactly happens when two galaxies are merging and what happens to the stars and to the gas and to the black holes. And these are some of the best simulations in this area that have been done by actually a joint US-German group. Volker Springel is a German astrophysicist, but Lars Hörnquist at the Center for Astrophysics in Harvard is also heavily involved. And so what you see here on the left side are the stars, and on the right side the gas. That is the fate of the gas at this merger when you are actually really putting in the detailed physics. And by the gravitational interaction between the two galaxies, gas is driven into the center of these two galaxies, and the black holes are actually then happily eating that gas, but they are also, by these jets and by the matter that they are ejecting, putting out such a large pressure that we now believe that during this merger process, while the stars are forming one beautiful big new galaxy, the black hole is actually, the merging black hole is pushing out the gas. And so that's the reason why after a galaxy merger you are ending up with an elliptical galaxy, which is a red and dead galaxy which does not have any gas inside. And it turns out that the black holes are actually playing an extremely important intimate role in how galaxies are allowed to evolve. There is an intimate relation between the black hole in the center and then the stars and the gas of this galaxy. And that relation has to be put into our theories in order to understand how galaxies are evolving. And so what we believe is that when you start in the early universe, you start to form a galaxy. The galaxy is growing by accreting matter, But the black hole in the center, there must be somewhere a black hole when the very first star has turned into a black hole, and one of these black holes is in the center of the galaxy. That black hole in the center is then happily eating accreting matter, and is within a relatively short time is growing so much that it turns into an extremely massive object, a so-called quasar. And the highest redshift quasar, I already told you, is around a redshift of 7.1. And so in the early universe, we believe that already the seeds of the black hole that we are seeing in the center of today's galaxies have actually been put in there. But the big question is whether these black holes, I will come at the end of my talk, we can in principle explain how a black hole can grow from 100,000 solar masses to about 10 to the 9 solar masses that we are seeing in these early quasars. We still have a big question mark down there, how the black holes can actually grow from a stellar mass to about 100,000 solar masses. But if you put in all of these detailed physics and all of these simulations, the big trick how you can actually feed matter into a black hole very efficiently is that you have galaxies which are already very compact groups that are already very compact together. Each of these little galaxies already has a black hole in the center, and then when you merge them, you can feed mass into this black hole very, very efficiently and quickly, and you can grow the very, very early, extremely luminous, happy, shining black holes that we are seeing as the quasars in the early universe. Now, I come to the last chapter. Can I still use 10 minutes? Okay. Cosmic evolution of black holes. I have spent, together with my colleagues, Martin Schmidt and others, quite some time in trying to understand how these black holes actually grow, how they evolve in the cosmic time. And we have used a lot of the Keck telescope also in order to understand this effect. The sky is filled with a diffuse X-ray emission, which we call the X-ray background, that has been discovered in 1962 by our colleague Riccardo Giacconi, who got the Nobel Prize for this discovery. And in the meantime, we know that this diffuse X-ray emission is actually coming from a very large distance. Here, you can see a picture that we have taken with the ROSAT satellite of the moon. And you see the moon is shining in the X-rays in the same way as in the optical, but you see that the dark side of the moon is actually casting a shadow on the X-ray background, which is behind the moon. And so we have actually measured the whole sky radiation of that X-ray background, and we have then taken X-ray telescopes, first ROSAT, and then later XMM Newton, and then Chandra, finally the most recent picture from Chandra. We have been resolving this X-ray background into individual point sources, hundreds and thousands of individual point sources, and it turns out with optical spectroscopy that we did from the Keck telescope that we could find that all of these point sources that are making the X-ray background are actually black holes in the distant universe, and what we are seeing there is the radiation, the echo of the radiation that the black holes have produced when they were actually growing and eating. So the X-ray background is giving us a very important information about how much light has been produced by black holes throughout the life of the universe, and how black holes actually have grown, when was their best time, so to speak, to grow and live. And so, in particular, in the recent years, we have focused on one area in the sky which is about 10 times larger than the full moon. It is the so-called Cosmos survey, and it has been observed to death by almost all telescopes, including Subaru and Keck on Mauna Kea. And we have also observed the same field with the XMM Newton spacecraft. And again, we have found about 2,000 black holes in a tiny spot on the sky. And if we extrapolate these numbers, then we can say that there must be on the order of 200 million black holes all around the sky. And these are the black holes which we are seeing at the time when the galaxies were happily eating and happily probably growing. And so the data that comes out is shown here. I don't want to dwell into great detail, but what we see here when we are comparing that to the cosmic history is that the luminous quasars, the very, very massive, massively shining objects, they have been formed roughly after the first galaxies. So here the first galaxies are formed, and the quasars are formed at a redshift around 2 or 3, when the universe was about 1/3 to 1/2 of its current age. Whereas the normal, less luminous black holes, which are much more abundant, which are almost happening in almost every galaxy, they are coming much later. They come close to our home. And so what we are seeing in the quasars is a process that happens in the early universe very quickly, whereas in the X-ray sources we are seeing objects that are actually relatively late in the history of the universe. And what we are interested in, what we still have not fully understood, is what are really the very first objects. I mean, the quasars are something like the puberty of a galaxy when it was, so to speak, in its most active ages, in young ages. But we have not yet seen the birth of a galaxy and the very first stars and how they relate to black holes. And that is a very hot topic that I can actually spend one view graph at the end of my talk. So now we believe that we understand better the history of the evolution of galaxies. We have these mergers. They are producing a heavily buried, growing black hole. In the end, this black hole is shining very brightly and looks like a very, very bright quasar. And then this quasar, when this is dying out, what is left over is one of these round, empty elliptical galaxies. But then this is this famous picture of the Sombrero galaxy. When you are taking one of these elliptical galaxies and you wait long enough, then it is actually growing a disk around it again. And then this whole circle can start again. And so we are seeing X-ray emission of black holes in this very fast procedure when the black holes are really merging and are growing very quickly. But we also see X-ray emission in this period when the disk is growing around the pre-formed black hole, and the black hole can then still eat, but not as happily and as rapidly as in this merging process. So now I come to the question: what can we say about the earliest black holes? What in nature can give us access to the very, very early black holes? Computer simulations can tell us that the very early stars, that the very first star, this is a simulation of what we believe the very first star looks like, that these very early stars must have been much more massive than the stars that we now know in our universe. The most massive star that we know of has about roughly 100 solar masses. We believe that the very early stars have grown to about 1,000 solar masses or so. The main reason for that is because in the early universe there were not yet the normal matter, the metals, which are currently dominating the light of the stars, and therefore such a star can have actually grown much, much larger. And what we are looking here is actually a simulation of the very first star which was formed at the intersection of one of these filamentary structures where all of these filaments are meeting, and we are zooming into the center of a gas ball which is probably about 100,000 solar masses in mass. And the very center of this gas ball is probably a star of roughly 1,000 solar masses, and that's the very first star which actually has started to form. And it starts to shine on its own. It starts to produce, it starts to burn hydrogen in its center. And it is one of these extremely massive stars which only lives for a very, very short period of time, roughly 3 million years. And after 3 million years, this star is actually exploding in a supernova explosion. So it's one of these most massive stars which lives very short. This supernova explosion is blowing out the matter that the star has actually formed, the metals that have been formed inside that star. And this supernova explosion is then very likely also leaving the very first black hole in the center. So we believe, I believe that already the first star in the universe has also produced the first black hole. And this black hole is then sitting exactly in the center of what later becomes a galaxy. More and more matter will fall onto this center. It will form stars. The black hole will eat. And that is very likely the fate, so to speak, of the very first structure in the universe. In our local universe, this black hole is probably the center of M87, of the Virgo cluster that we have visited. And so this was probably the remnant of the very first star that was formed close to the center. Now we still need to explain how from this very first star we turn into objects of 10 to the 5 solar masses, 10 to the 7 solar masses, up to 10 to the 9 solar masses. This is still an area which there are many different possibilities that we don't quite know. And these objects are so far away that even our most powerful telescopes today, like the Keck telescope and so on, cannot really see these objects. We need, as I will show in the end, we need something like the 30-meter telescope to really pin through to the very first generation of stars. But before we do this, we can use one trick, which actually I have worked with a student, with a former student and now postdoc, Nico Capelluti. We can look at the imprints that these early objects make on the background in the sky. Every piece of light that has ever been produced is somehow frozen in the background. And what we have done is we have looked at the background radiation that is measured by Chandra on one hand. This is the X-ray background. And we have measured by the background radiation, we have measured the background radiation that has been produced in the infrared by stars. So what we are looking here is actually black holes. And here we are looking at the stars. And in both cases, in these images, we have excised all the real objects, everything that can really be discovered. So we are only looking at the imprint of the light that we cannot resolve. And lo and behold, we have found that this is actually has just been submitted. It's fresh from the press, so you are the first one to hear this publicly. We have found a correlation between the backgrounds of the near-infrared and the X-ray sky. And we believe that this may be the very first glimpse of the very first stars who have basically imprinted their light and their fluctuation light in the two backgrounds. And if you correlate the two backgrounds, then you can actually see the imprint of these first objects. In order to really study these objects, we need, as I said, the 30-meter telescope on Mauna Kea. And I'm very hopeful that in a year from now or so, we can already say that the TMT is on its way. We are still waiting for the final decisions, both financially and also in terms of the construction permit of the TMT. So keep posted. I think this is an extremely exciting field to look at. Now, my very last slide, I was promising you something about the fate of the universe, and I didn't talk a lot about the fate. I talked about black holes a lot, but what is the connection between the black holes and the fate of the universe? I already told you that the universe itself is almost a black hole. I told you that probably one of the first objects in the universe was a black hole. Now, the very last thing I have to tell you is that the last object in the universe is also a black hole. What is shown here is the completely unimaginable fate of the universe. So what we know already is basically the universe started as an extremely hot fireball. It expanded, it got colder and colder. Then the very first stars were formed, and then galaxies were formed. And today we are looking at all these colorful, beautiful things in the sky. This is 10 to the 10 years. The universe currently is 13 billion years old, which is roughly 10 to the 10 years. Now, if you take another 10 to the 10 and multiply it to the 10 to the 10, so this is a universe which is 10 to the 10 times older than our current universe. Not twice as old, not 3 times as old, 10 to the 10 times older. And this is 10 to the 20, 10 to the 30, 40, 50, 60. So it's a huge, unimaginable time span. And lots of things can happen in that time. What we believe that we know is that at some point there will be no stars anymore because all of the gas has been burned out. There will be no stars. The universe, the sky will become pitch black, everything has removed so far from us that anyhow the sky is becoming black. But then at some point, the protons will decay, and at some point the dark matter, which I didn't talk about at all today, will also decay. And so in the end, nothing will be left apart from the black holes, because the black holes, as I said, are the longest lived life form that we know. They live for about 10 to the 60, 70, 80, 10 to the 100 years. So the very first object that entered the stage of the universe was a black hole, and the very last object that will leave the stage of the universe will be a black hole. And in the end, nothing will be left, and it will be the same thing that was there in the beginning. The universe started from nothing, and it will end in nothing. Thank you very much.